I will begin with a word of prayer. Heavenly Father, we thank you for this day. I thank you for these students. Just ask you to bless this class today, Lord. In your name I pray. Amen. So the code's over there to attend. Today we're talking about, well, a variety of things actually, but I'm going to start with the hyperbolic functions. So, something I should mention that's, this is a general thing that's true. If you have a function which has a symmetric domain about the origin, you can write any function which, if the function has both x and minus x in its domain, right? So like every time you got 3, you got minus 3. If I got 50, I've got minus 50 in the domain. If the domain of the function's like that, you can always take such a function and rewrite it as a sum of an even function plus an odd function, all right? And here's how you do that. So f of x is 1/2 f of x plus f of minus x plus 1/2 f of x minus f of minus x. Now, see, this will make sense provided f of minus x is defined whenever f of x is defined, right? This is a kind of just a sneaky formula, right? Like, look at it. So 1/2 plus 1/2 is 1, right? And we're just adding and subtracting the same thing. But if you study this, if you replace x with minus x, the first thing is unaltered. So this part of this identity is even. It's an even function. And this right here, if you replace x with minus x, you can actually see that that's an odd function because it'll give you back minus what you start with. All right? This is a general identity. But something especially interesting happens when we apply this general identity to the exponential function. See, e to the x, does e to the x have a domain which is symmetric about the origin? I mean, what's the domain of the exponential function? Yeah, it's the whole real line, right? What's the range? Yeah, positive numbers, right? It never hits 0, but it hits every beyond that. Okay, so, this is 1/2 e to the x plus e to the minus x plus 1/2 e to the x minus e to the minus x. So those are respectively the even and the odd parts of the exponential function. So this, by definition, is the hyperbolic cosine, right? And this right here, by definition, is the hyperbolic sine. But I understand these, in particular, as just being the even and odd parts of the exponential. All right? So that tells you something about their graph, right? Like, what's the graph of Cosh look like? And what's the graph of sinh going to look like? So what about Cosh? Could it be negative? It's adding exponentials together, right? It's adding positive things together. In fact, if you study it, the smallest that it is 1, and that happens at 0. All right, we'll prove this with calculus here in a bit, but essentially the graph looks like this. That's not quite doing it justice. I mean, it's exponentially growing on both sides, all right? So, but roughly speaking, first glance, it kind of looks like the graph of x squared plus 1. The smallest it ever is 1. It's never 0. Sinh, on the other hand, is an odd function, so that means it has this kind of shape, right? I mean, it doesn't mean that necessarily, but if we look at sinh, what can you tell me, like asymptotically? What happens as x goes to infinity? How about this? For x much, much bigger than 0, we have cosh of x is approximately what? And sinh of x is approximately what? So one important idea when you're thinking about how to understand the graph of a function is to think about like asymptotics, right? Like what happens when x is really, really large or really, 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 really negative, right? Far away from the origin. So you guys tell me, looking at the definition of Cosh here, what happens when x is really, really large? What about e to the minus x? So let me just put in parentheses here the key intuitive idea, which is that e to the minus x is approximately 0, and for this e to the x is approximately 0, right? If x is very, very negative, then the exponential of x is very close to 0, and vice versa. So as I look at these formulas, what's Cosh x behave like? Cosh x is essentially just what? E to the x over 2, right? In this case, and sinh x is also e to the x over 2. So if I did these pictures justice, like, after a while, the fact that it's shifted up by 1 doesn't really matter, and Cosh and sinh kind of look more or less the same for really, really large x. They're both just exponential growth. But for very negative x, Cosh x is approximately e to the minus x over 2, right? And sinh x is minus e to the minus x over 2, which is this guy here, all right? So that's the basic graph of Cosh and sinh. They're even and odd. How many zeros does Cosh have? None, right? How many zeros does sinh have? Just 1, right? Now, the basic calculus is what? d dx of Cosh x is what? d dx of 1/2 e to the x plus e to the minus x. And then what do? Pull out the half and do the chain rule. For the second piece, we get that minus from the chain rule. And what do you got? That, by definition, is the hyperbolic sign, right? So the derivative of Cosh is sinh. And vice versa, right? If you differentiate the hyperbolic sign, what do you get? Sorry, I have written below the head of someone. Getting someone in the very back of the room, a lot of stretching. I guess I should probably have you guys do stretches before class just to make sure no one hurts themselves. I'm going to write at the bottom of the board. All right, so on the flip side, d dx of sinh x is Cosh x, all right? So where is the hyperbolic sign increasing? What can you tell me about hyperbolic cosine? It's the sum of positive things, right? So in fact, it's what? It's positive. So you could easily observe that this is greater than or equal to 1, thus f of x equals to sinh x is increasing, right? How about Cosh x? Is Cosh x increasing or decreasing? You're like, I don't know. It depends on the context, right? Sometimes it's decreasing, sometimes it's increasing. It's increasing for positive x, and it's decreasing for negative x, right? All right. What else can we talk about? What are the basic identities for Cosh and sinh? Well, you know that sine squared plus cosine squared is 1. We learned that last time, right? Actually, you should reject that. You should say, I learned that many years ago in a simpler time, right? It wasn't a simpler time. Is this a simpler time? It's a personal question. I don't know. So what are the identities for Cosh and sinh? Can you tell me any? I mean, one of the fundamental identities I've already written on the board is a motivation, which is that the exponential, right, is cosh x plus sinh x, right? So there's an identity which is true. What about, hey, it was interesting yesterday to look at the imaginary exponential and look at theta versus minus theta, right? Maybe we should look at e to the minus x. What's that look like? We get what? Cosh of minus x plus the sinh of minus x by substitution. But what did we just say about cosh and sinh? Cosh is what? Even, and sinh is odd. What does even function mean? It means that the minus gets absorbed, right? And the odd means that the minus does what? It factors out, right? So this is what? Right, cosh x minus sinh x. How are e to the x and e to the minus x related? What happens if I multiply them? So, okay, so I mean, of course, we can write that's cosh x plus sinh x, right? Times cosh x minus sinh x. That's like a plus b times a minus b, right? Which is factoring the difference of perfect squares, a squared minus b squared. So we multiply that out, the cross terms cancel. We should get what? We should get cosh squared minus sinh squared on the right-hand side. Yeah? Now, if you'll allow me this manga-style comment, in other words, I'm working in this direction, yes, as you read fine comic books, yes? So this is e to the what? Laws of exponents, right? E to the x minus x, which is otherwise known as e to 0, also known as 1, right? So what do we have? Aha! We have that cosh squared x minus sinh squared x equals to 1. Very cool. This is the analog of the Pythagorean identity for sine and cosine. All right? What could we do to this identity to discover perhaps other identities, maybe? I mean, one fun thing we could do would be to differentiate it, see what happens. What happens if we differentiate this identity? How would you differentiate? So I would get what? I would get 2 cosh x sinh x, right? Minus 2 sinh x cosh x equals to d dx of 1, which is equal to, of course, 0. Do you understand why I have what I have? I was doing, it's a square function and then the chain rule, right? So twice the function times the derivative of the function. The inside function is respectively cosh and sinh, which gives me sinh and cosh. And what I just wrote down in blue is true, right? But useless, right? Because we have just derived 0 equals to 0. Seems like it's safe to say, right? But maybe this doesn't really give us a lot of more insight about how to work with sinh and cosh, right? So sometimes you differentiate something, you don't get anything, you know? This can happen. All right. So maybe we should try a different approach to find new identities for cosh and sinh. How about if we just look at cosh squared directly? Maybe we can find something for cosh squared. What's cosh squared x going to be equal to? Let's see if we can find an identity for cosh squared. So this is 1/2 e to the x plus e to the minus x, quantity squared. There is a big difference between what I'm doing right now versus what I was doing yesterday in the sense that there's no imaginary unit, right? It's just e to the x and e to the minus x. So we get what? We get 1/4, right? And then what happens when you square this? You get e to the x squared plus e to the x, e to the minus x, plus e to the minus x, e to the x, plus e to the minus x squared. But you guys know laws of exponents, right? So like the middle two terms are just what? Yeah, there's a 1 and a 1, right? So these two guys together give me a 2, right? And so what do I have? I've got 1, so 2 over, I'll leave it, 1/4 times 2 plus e to the what? E to the 2x plus e to the minus 2x. Can we simplify that? In this discussion, what's interesting is to bring things back to hyperbolic sine and cosine, right? Because they have such a nice behavior and interrelation in terms of calculus, right? There's something to be gained there. So, I mean, yeah, that's a nice formula. It's exponential is great, but we can do better. So what I would do is I would factor out a half, and that gives me a 1 plus 1/2 e to the 2x plus e to the minus 2x, right? What is that?
So does the 1/4 just disappear then?
No, it just distributes. This is a half times a half, which is a 4th.
And then you
Yeah. But what the reason I pulled that half inside, yeah, is that this is what? Yeah, that's Cosh 2x. And so what do we have? We have 1 plus the hyperbolic cosine of 2x. Essentially, the same calculation with imaginary exponentials shows that cosine squared theta is equal to 1/2 of 1 plus cosine 2 theta. Right? Just comment. If you look at cosine squared theta as 1/2 e to the I theta plus e to the minus I theta, you do essentially the same algebra. You get 1/2 of 1 plus 1/2 e to the I theta, 2 I theta, plus e to the minus 2 I theta, which of course is 1/2 of 1 plus cosine 2 theta. There's like a beautiful analogy to be seen here. Yep.
For Cosh minus sinh equals 1, where does the 1 go when we get up here?
Cosh squared minus sinh squared. Oh, no, I did not jump from the green to the blue up there. Like that is just the definition of Cosh squared. So Cosh, remember, is this. So I'm just taking this expression and just squaring it. And that's what this calculation is up here. So we can derive that hyperbolic cosine squared is 1/2 of 1 plus Cosh 2x just directly, just with ordinary laws of algebra. Now, once we know that, I think we can derive the identity for sinh pretty easily, right? So, setting this comment aside, we have that Cosh squared x is equal to what? I think if we differentiate that, what do we find if we differentiate this? We get 2 Cosh x sinh x, right? Equals to what? 1/2 of 0 plus 2 times the sinh of 2x. So what do we find here? We find that sinh of 2x, right, is equal to 2 times cosh sinh. What did we see yesterday? We saw that what? The sine of 2 theta was 2 sine theta cosine theta, right? So sometimes the identities, like the analog between the trigonometric identity and the hyperbolic identity, is just direct, right? Like, look, I mean, you see what I'm saying? This cosh squared equals 1/2 1 plus cosh 2x is really just straight analogous to the cosine squared equals to 1/2 of 1 plus cosine 2 theta, right? But you got to be careful. They're not always the same, right? We just saw that with cosh squared minus sinh squared, right? It's not cosh squared plus sinh squared. It's cosh squared minus sinh squared. That's 1. So we have to work through things. We have to be careful. There are more identities which are known for cosh and sinh. Let's see here. We could, well, I think that's probably enough for our purposes. I mean, there's adding angles, adding angle formulas for like cosh. For example, cosh of alpha plus beta would be what? So if we're let me do sinh. Let me do sinh. Sinh. And I think that the identity is just like it usually is, which is that it would be sinh alpha cosh beta plus sinh beta cosh alpha. Yeah, we could work this out. I mean, go to the definition of cosh and sinh and verify it. Here's a quick check on it being correct. If I put alpha and beta both equal to x, what happens? If alpha and beta are both x, I get sinh of 2x, right? And that's sinh x cosh x plus sinh x cosh x, which is what I have above. So that shows me that I've remembered it correctly. It's just, I mean, of course, to be sure, you can actually put in the definition of cosh and sinh in here and multiply it out. What ends up happening is you get a plus term and a minus term, which cancel out, and I think you're just left with the, oh, let me shut up. So, and then what happens if we differentiate this? If we differentiate with respect to, let's say with respect to alpha, we get what? Cosh alpha, cosh beta, plus sinh beta, sinh alpha. So you see there's a difference in this one. Right, the distinction is that with sine and cosine, we have a minus from the derivative of cosine, right? And that's why there's a distinction in the sine adding angles versus the cosine adding angles formula. But I think for a hyperbolic, we get plus for both. All right? How about sinh squared x? What would that be? One way we could derive the identity for sinh squared would be to use that sinh squared is what? Sinh squared is actually equal to cosh squared minus 1, right? Am I right? Yeah, so just solve that for sinh squared. But we just learned that cosh squared is what? 1/2 of 1 plus the hyperbolic cosine of 2x minus 1, right? And so if you do the math, what do we got? Well, that's kind of interesting. that looks a little bit different than what we've seen so far, but there it is. Sinh squared x is in fact 1/2 hyperbolic cosine of 2x minus 1. All right, those are the basic things we know about hyperbolic sine and cosine in terms of identities. What do you think is next? So you start trigonometry by talking about sine and cosine. What do you talk about after that? Start talking about like secant, cosecant, tangent, these other things, right? In the same way, we can talk about hyperbolic tangent, right? So what do you think hyperbolic tangent's going to be here? What would tangent be defined as? Right? And what would the derivative of hyperbolic tangent be? Well, let's not just guess. We can work it out, right? We just need to know the quotient rule, which you guys know, right? So what do we got? We have Cosh x minus sinh x divided by Cosh. Oh, looks like we have a winner because someone told me it must be hyperbolic secant squared. I think you are correct, but I believe that was on the basis of guessing, yes? Okay. Yeah, guessing will get you a certain amount, as long as you're right. This is Cosh squared minus sinh squared, right? Which we just learned is 1. So we're looking at 1 over Cosh squared, which is hyperbolic secant squared. Because, by the way, definition, hyperbolic secant of x is 1 over Cosh. And while we're at it, the hyperbolic cosecant of x is 1 over sinh. And while we're at it, the hyperbolic cotangent of x is Cosh x over sinh x. So you get your sesh, your Cosh, and your coth. I don't know. I have really no good abbreviations for these things. I just call them hyperbolic secant, hyperbolic cosecant, hyperbolic tangent, cotangent, yeah.
Are there inverses to these functions?
Ah, yes. The inverses to these functions would be the next chapter in this story. A good question. So my question to you at the moment would be, what can you tell me about tanh? Like, what can we see from this formula? But there are inverses. Yes, we need to talk about that. If it's 1 over Cosh squared, is that defined everywhere? What's the domain of hyperbolic tangent? Is there any x which makes this formula go haywire? We're still allowed to say haywire, right? That's not like some sort of secret politically incorrect phrase, is it? I don't know. You never know. All these things we've learned to say, there's no telling what kind of trouble you can get yourself into. No, Cosh is what? Smallest is 1. So there's no division by 0 here. The domain of the hyperbolic tangent is the whole real line. And from this, I can see that the derivative of the hyperbolic tangent is 1 over a positive function. Well, it's 1 over the square of a non-zero function, right? So this is just straight up positive everywhere. So the hyperbolic tangent is everywhere increasing. What's its graph look like? So I wrote the hyperbolic tangent is sinh over Cosh. How else could we express that? Yes, sir?
I don't really know what like a hyperbolic is. Like,
Yes, that's what we're learning today. So they're defined right here. Cosh is 1/2 e to the x plus e to the minus x. And sinh is 1/2 e to the x minus e to the minus x.
like that's definition of. Okay.
Yeah, that's it. Their definitions are right here. They're the even and odd parts of the exponential. But yeah, we usually cover this in Calc 1, but Dr. Sprano said there was snow or something. Oh, for some reason we had a 13-week semester last semester. I don't know how that happened. Anyway, So here we are. This is 1/2 e to the x minus e to the minus x, yeah? And this is 1/2 e to the x plus e to the minus x, again, using the definition. The halves cancel. And if you look at that formula, you can gain insight into what this looks like asymptotically, right? So this is, there's two different ways we could write this. On the one hand, we could write this, let's see here, so cancel the halves and divide the top and the bottom by e to the x. So we could have 1 minus e to the minus 2x over 1 plus e to the minus 2x. It's also equal to e to the 2x minus 1 over e to the 2x plus 1, right? So you can either multiply the top and the bottom by e to the x, or you can multiply the top and the bottom by e to the minus x, all right, after you cancel the halves. Both of the expressions I just wrote down are true, and they're both useful for thinking about the graph, right? So like, if I'm thinking about x being very, very large, which one of these should I probably think about? I would suggest that we use this one to think about x being much, much greater than 0, right? If x is much, much greater than 0, e to the minus something is really, really small. It's negligible, right? So we really just have like 1 plus 0 over 1 plus 0. So asymptotically, for very large x, this is approaching 1, right? It's approaching 1. Yeah.
Question. When you went from the 1/2 e to the x minus e to the negative x to the circled one,
Yeah.
in the blue,
Mhm.
what'd you do exactly?
I multiplied the denominator and the yeah, you're saying something?
I think, yes, you were saying you were going to multiply it. What did you multiply it by?
E to the minus x. So e to the x and e to the minus x cancel. They give us 1. And e to the minus x times e to the minus x gives us e to the minus 2x.
And then you split.
No flipping.
You went from negative 2x to 2x on the bottom.
Oh, I have to multiply this by e to the, you know, oh, to go from here to here?
Yeah.
Well, let's say to go from here to here, I multiplied by e to the x over e to the x. So when I do that, it makes these turn into e to the 2x, and it cancels these guys to give us minus 1 and 1, respectively. Yeah.
Why would you multiply by 1? Why did you do that?
Oh, well, stick with me. I did that so I can see what the expression looks like for large x. Like if I have e to the x and e to the minus x, it's hard to see what's dominate, what the behavior is. Once I rewrite it that way, I can clearly see that it's tending to 1, right? But on the other hand, when x is very, very negative, the lower expression, right, when x is much, much less than 0, when x is negative, and really, 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 really negative, these are like negligible, and we essentially just have minus 1 over 1, which means as we go over that way, it's tending to minus 1. So what I'm trying to get at here is the graph of the tangent looks something like that. It's everywhere increasing, right? And it asymptotically goes to 1 or minus 1. What's the range? What's the range of the hyperbolic tangent then? Negative 1 to 1. Now, why does that matter? Because the gentleman in the second row asked me about inverse functions a second ago, right? So in order to have a clear understanding of inverse functions, we have to have an understanding of what's the range and what's the domain that we're interested in, right? What do we need to have an inverse function for a function? Do you guys remember? I'll remind you. To define an inverse function, we need to have a function which is 1 to 1, right? The function has to pass the horizontal line test so that we can make an inverse function. Now, if the function does not pass the horizontal line test, like this one, right? See, Cosh is not 1-to-1 because Cosh of x is equal to Cosh of minus x, right? So if we're going to talk about an inverse function for hyperbolic cosine, that means we're going to talk about what's called a local inverse function, right? You already have a lot of experience with that because trigonometric functions don't have inverse functions, not globally, right? When we talk about inverse sine, we talk about inverse cosine. Are those inverses for the full sine function and the full cosine function? No, certainly not, right? I'll remind you. So sine, if we go from pi over 2 to minus pi over 2, this part of sine has inverse sine as inverse. Right? What's the domain of inverse inverse sine? Right, -1-to-1. That's the range of sine. And what's the range of inverse sine? The range of inverse sine is minus pi over 2 to pi over 2. Why is that? It's our convention to make inverse sine, the inverse for sine, restricted to minus pi over 2 to pi over 2. Likewise, inverse cosine is actually the inverse for just this part of cosine, right? So if you wanted me to be pedantic about it, inverse sine x is really kind of a lie. If we were to be more honest, instead of writing inverse sine, we would say something horrible like this. It's the sine function restricted to minus pi over 2 to pi over 2, that function inverse. Because honestly, it's not the full sine function that inverse sine is the sine of the inverse function to. It's just that part of sine, right? And that's why when you punch in inverse sine into your calculator, you always get back minus pi over 2 to pi over 2, right? Likewise for inverse tangent. Inverse tangent is the inverse to tangent between plus or minus pi over 2, right? And by definition, inverse cosine, it's the inverse to cosine from 0 to pi. Now, for hyperbolic sine, this is not an issue, right? Because hyperbolic sine is increasing everywhere. It's 1-to-1 on the whole reals. So when we talk about inverse, we can talk about inverse hyperbolic sine without qualification, right? So definition, sinh inverse of x is the function with sinh of sinh inverse of x equal to x and sinh inverse of sinh of x equal to x. It's just the inverse function. There's nothing funny going on here. And pretty much the same is true for hyperbolic tangent. Let me write that up here. So, definition inverse. So we write tangent inverse is the inverse function to hyperbolic tangent given by the following relations. Hyperbolic tangent of inverse hyperbolic tangent of let's say y equals to y, and inverse hyperbolic tangent of hyperbolic tangent of x is equal to x. Now, I need to use a different letter for this one. Perhaps I should also use a different letter for this one down here as well. The reason I say use a different letter is because it doesn't matter, because if I put y and y here, it doesn't really change much, because either way, both of the above and below equation have to be true for all variable values. But how about over there, inverse hyperbolic tangent? What should x be allowed to range over versus what should y be allowed to range over here? So conceptually, the domain of the inverse is the range of the function, right? So we just learned that the range of hyperbolic tangent is what? Negative 1 to 1. So the y should be between minus 1 and 1. All right? But here, x is where? What can x be? Right, x is anything. Just a real number. So that's the definition of inverse hyperbolic tangent. There's the definition of inverse hyperbolic sine. And what else is there? Inverse hyperbolic cosine. How are we going to... There we got to make a choice, right? Because it's either got to be the inverse with respect to like this piece, or it's got to be the inverse for this piece. So the custom is to let it be inverse for the positive branch, the positive part of the hyperbolic cosine. So here it is. Cosh inverse is actually equal to hyperbolic cosine restricted to 0 to infinity inverse. Now, I'm using some notation that you probably haven't seen before, and it's probably not going to be a big deal for us in here if you don't know it. But let me just explain to you what I mean. If we have a function, that goes, say, from A to B, then I can talk about f restricted to, say, v, which is going to be a function from v to b for any v which is a subset of A. So like a restriction of a function is, the same formula works. We're just taking the domain and like making it smaller. So we're that's what's at play here when we were defining inverse hyperbolic cosine. We're throwing out the negative part and just looking at the positive part to find an inverse. And anyway, let me just get to the point. Cosh inverse of cosh of x is equal to x, and cosh of cosh inverse of y is equal to y. But here's the rub. It's not for all x. It's actually just going to be for x greater than or equal to 0. And here, what's the domain of inverse hyperbolic cosine? It's the what? It's the range of hyperbolic cosine, which is what? One to infinity. All right. So that's hyperbolic functions in a nutshell. Now, gentleman in the second row probably still wants to know how on earth we differentiate these things, right? Like, what's the derivative of inverse hyperbolic cosine? What's the derivative of inverse hyperbolic tangent? How are we going to figure that out? Well, there are a couple different approaches. I think the easiest approach is to use implicit differentiation, and the way we did it for inverse tangent last time, right? So if I want to figure out what's the derivative with respect to x of, say, inverse hyperbolic sine, then a simple way to figure this out is to say, okay, well, y is equal to inverse hyperbolic sine, right? And then what I do is I take the sinh of both sides. All right? So sinh of y is equal to the sinh of the inverse hyperbolic sinh of x, which is just what? That's just x again, right? You know, it's annoying, but this notation is a little bit dangerous. You know that? Inverse tangent is not equal to 1 over tangent. Yet, tangent squared is equal to the tangent of x squared. You know, I always try to stop and mention that at some point as I'm talking to you guys, because it's an important distinction to make. I mean, this notation is not quite level, right? I mean, it's not consistent. It's kind of hypocritical in some sense, right? For that reason, some people use arctangent, like a tangent, rather than doing tangent inverse. But tangent inverse is hardwired into my brain. I can't undo it, and it's in most books. So I don't think I do you any favor by not using inverse tangent, like as is usually denoted. Just beware that inverse tangent, this is cotangent, which is an entirely different function altogether. All right? So beware of this. Now we've had the talk. What can we do with sinh y equals to x? What's our next move here? We differentiate both sides. What's that give us? We get cosh y times dy dx, right, equals to 1. And then, well, dy dx is what I'm after, right? I'm trying to figure out what's the derivative of inverse hyperbolic sine. So I solve for dy dx. And this gives me dy dx equals to 1 over cosh y. But at this stage, I need to remember cosh squared y minus sinh squared y is equal to what? Yes, sir?
Where'd you get the cosh y? Like that equation that cosh y dy over dx equals 1.
So differentiating implicitly, it's right here. So take that, I differentiate with respect to x, I get this. No? I mean, ignore the middle. We're just differentiating this side, and that gives us cosh y because derivative of sinh is cosh. But then because we're differentiating with respect to x, we multiply by the derivative of the inside function, which is y. So cosh y dy dx. And then the derivative of x is just 1. So it's, yeah. If you're trying to do something differentiating this, no. Don't do that. All right, so this Pythagorean identity, what's this give us for cosh squared? We get 1 plus sinh squared y, yeah? So what can I do? Oh, but what is sinh? Y, x is equal to sinh y, right? So this is equal to 1 plus x squared. And so what do we have? We have 1 over the square root of 1 plus x squared. See, because if cosh squared y is equal to 1 plus x squared, then the square root, right? Square root of cosh squared y equals to the square root of 1 plus x squared. And this is cosh y. Why is that true? Well, there is a rub there, right? I mean, generally speaking, the square root of x squared is what? Nope. Yeah, it's absolute value of x. See, if I took the square root of like minus 5 squared, minus 5 squared is 25. The square root of 25 is 5, right? So then, in that case, it comes out to minus x as it happens. So it's absolute value of x. But why don't I have to worry about that? What do we know about hyperbolic cosine? Hey, it's always positive, right? So the absolute value of hyperbolic cosine is always hyperbolic cosine. So there's no loss of anything here by just simplifying that to Cosh y. It's correct, all right? So there you go. The derivative with respect to x. Yes, sir?
How did the sin squared of y become x squared?
See, y is equal to x up there. Just plugging that in, and x squared is x.
I will color code her comment. So what I'm learning is I should have written this somewhere as to not lose you guys. There we go. Which is fine. Questions are good. Yeah. So there you have it. The derivative of inverse hyperbolic sine is 1 over the square root of 1 plus x squared. Which is kind of neat, right? Because now if I give you integral of dx over the square root of 1 plus x squared, you're like, that's stupid. That I can do that. That's just inverse hyperbolic sine of x plus a constant. Yay, done. We just gained an elementary integral, which is far from obvious. It's kind of neat. What would the derivative of inverse hyperbolic tangent look like? So let's go through the same song and dance. We write y equal to inverse hyperbolic tangent of x. And then what do? Take the hyperbolic tangent of both sides of the equation, right? So this gives me that tanh of y is equal to x. Agree? Make sure everyone agrees before I go on. Right. Take the tanh of both sides, right? Like tanh is the natural enemy of inverse hyperbolic tanh, right? If inverse hyperbolic tanh is walking down the streets and he sees tanh coming, it's like, no! Sorry, it's horrible. So now we differentiate with respect to x, right? Implicitly. And what's that give us? It gives us hyperbolic secant squared y times dy dx is equal to dx dx is equal to 1, right? Which tells me that dy dx is equal to 1 over hyperbolic secant squared y. We have got almost all the identities we needed today, but we need another one. How would you derive an identity for hyperbolic secant and hyperbolic tangent from the Cosh squared minus sinh squared identity? So if we divide by Cosh squared, what does it give us? It gives us 1 minus the hyperbolic tangent squared y equals to the hyperbolic secant squared y. So just divide the sort of Pythagorean identity for Cosh and sinh by hyperbolic cosine squared, and we get that. So this is the analog of the secant tangent identity, all right? And that's pretty cool because this, in the current discussion, is 1 minus x squared. So there you have it. The derivative with respect to x of inverse hyperbolic tangent of x is 1 over 1 minus x squared. Hooray! There is a stone cold formula for you. Now, going forward in the course, I don't always remember what I'm about to write down. So, I mean, there are places where I'll forget about this formula and like not use it, but it is there. But it does have some strings attached. What x is this true for? What's that? Not 1 is true. What was the domain of the inverse hyperbolic tangent is really my question. -1 to 1, right? So this is for -1 to 1. Very good. So in that context, we have the following formula. Right? In probably next week, we'll learn partial fractions decomposition, and we'll find a different way to integrate this, which will give us a formula which doesn't have quite these strings attached. But there it is. Now, I should mention to you guys, there are surprising and non-obvious relations, I would say, between the inverse hyperbolic functions and the logarithmic functions. You can actually rewrite the inverse hyperbolic functions as logarithms of algebraic functions. Let's derive one of those. So here, I'll do it for you. If we're looking at inverse hyperbolic sine of x equals to y, I'm going to show you how we can rewrite this as a logarithm. I don't think that's at all obvious at the moment, but let's get to it. Here's how you do it. So we take the sinh of both sides. I get sinh of y is equal to x, but this is 1/2 e to the y plus, minus e to the minus y equal to x. Then I do something kind of weird. I multiply by, well, this will not be weird. I'll just multiply by 2. Now I'm going to multiply this by e to the y. That gives us e to the 2y minus 1 equals 2x e to the y. And then I will rearrange things into something that you might recognize. So this gives me e to the y quantity squared minus 2x e to the y minus 1 equal to 0. Yes, oh what? It's quadratic in what? It's quadratic in e to the y. So we let lambda, let's say, equal e to the y, and we have lambda squared minus 2x lambda minus 1 equal to 0. At this point, I will complete the square. So that's lambda minus x quantity squared minus 1 minus x squared equal to 0. So I'm just completing the square. And so that gives me that lambda minus x quantity squared is equal to 1 plus x squared, which is pretty because 1 plus x squared is non-negative. Well, excuse me. Yeah.